does is essentially say, look, there's a set of realities from psychology that we ignore in economics. Behavioral economics is about how can we build models to bring in what we know is true from psychological research. And the best example of this is models of what we call time inconsistency. This is the best example of how we bring in an important insight from psychology in a manageable way into our models. Okay? So the idea of time inconsistency is that a widespread phenomenon that is not only always shown in psychological experiments, but in fact never rejected in psychological experiments, is the human problem of self-control. The human problem of self-control. We have a problem controlling ourselves. Okay? And what does this mean in economic terms? It doesn't mean that individuals are irrational. It doesn't mean that the models we wrote down and the optimization assumptions we make are necessarily wrong. What it means is, while we can make optimal plans, we can't carry them out. So in other words, think about the optimization problems done so far as having two parts. You make an optimal plan, then you carry it out. We haven't separated those. We've just said you decide how many cookies in pizza, eat that many cookies in pizza. But in fact, there's two steps. First, you got to decide how many cookies in pizza. Then you got to eat that many cookies in pizza. And you might think, well, that's sort of irrelevant. The second step, it's trivial. But it's not. It's not trivial whenever there are costs and benefits that differ in time. Okay? And when there are costs or benefits that differ in time, this can lead to self-control problems. In particular, when you have a decision that imposes a short-run cost for a long-run benefit, humans will undertake that activity. When you have an activity that imposes a short-run cost, long-term benefit, humans as a species, I don't know, maybe other species too, will undertake that activity. So for example, smoking. If you're a smoker, 90% of smokers, when surveyed, say they'd like to quit. Yet 90% do not quit. Why? Because when you wake up in the morning, you feel awful until you have that cigarette. You have the cigarette, and you're like, OK, I'll have a smoke till I'll quit tomorrow. OK? The idea of I can quit tomorrow, I'll solve that tomorrow, that's a standard feature of self-control problems. Let's think about savings for retirement. In our model of retirement savings, we had someone deciding across C1 and C2, and they just optimized with some indifference curve and budget constraint. We're not saying any of that math was wrong. We're just saying in practice, it's actually hard to put the money away and save it. Because in practice, once you have the money, there's a lot of attractive stuff. I talked about how, gee, when you get the job, you start saving right away. But right away, when you get the job, you want a new car, and you want to party, and things like that. So it's hard to say, well, yeah, I'm going to save for 50 years from now, so rather than going to the party tonight. Okay, maybe not. Once again, hard to teach in this crowd. We're all a very sort of self-controlled crowd relative to most Americans. But I think we all have experience with this. Okay, think about dieting or exercise. Things where with dieting, there's a short-run cost. You cannot eat that piece of cake, which is delicious, for a long-run benefit. Exercise, the short-run cost, which is you've got to go work out. It takes time. It takes effort, for a long-run benefit. Now, once again, you all look very fit. Maybe you don't feel that way about dieting and exercise. But we all have things we have self-control problems over. Mine is biting my nails. I cannot stop biting my nails. I'd like to stop biting my nails. I make plans to stop biting my nails. But when I've got a deadline of paper or my favorite team's on TV, I bite my nails. Okay, I've tried things like this. You can paint on your nails to make them taste terrible. It just tastes terrible when I bite my nails. Okay? I have a self-control problem. We all humans, not all humans, most humans suffer from self-control problems of one or another. So the question is, how do we build that into the models we use? How do we take the kind of parsimonious model we've used and add an element of time inconsistency? Well, let's come back to the intertemporal choice model we had before. The intertemporal choice model was someone trading off consuming today versus consuming tomorrow. And let's make that, rather than today versus tomorrow, let's make it the whole future. Let's make someone's decision. Let's say that someone has a utility function that depends on the entire future path of their consumption. Okay, all that matters for my utility is consumption, but the entire future path. But here's the key thing. Let's also remember we learned about discounting, that I care less about the future than I care about today. Okay? This is, remember with NPV, we talked about how money today is worth more than money in the future, which is why people would save. The reason people don't save is because I care more about today than I do about the future. In other words, humans have an inherent discounting of the future that offsets the return to saving. Putting money aside today is a benefit, you get more tomorrow, but it's a cost, which is we'd rather have shit today than tomorrow. That's the human nature. We call that discounting. And the way we typically model this is we say, look, we can model your utility as the sum from today till the end of time, till you die, of your consumption in each period. Let's say you're going to consume the same amount every time. Let's say consumption's smooth. So C is constant. Let's just say you're going to consume the same amount forever, times delta to the I minus T. Delta is what we call a discount factor. Delta is less than 1, greater than 0. It's the discount factor. It's how much less I care about consumption in the future. Okay? So for example, if delta is 0.9, then that says consuming something next year makes me 90% as happy as consuming it today. Consuming something in 2 years, and we assume delta by this functional formulation is exponential. Okay? So we assume consuming something in 2 years is 0.9 squared, so it's 0.81. Okay? So basically, we assume that exponentially, every period in the future is worth less. So next year is worth 0.9 of today, 2 years is 0.81 of today, etc. So we assume that basically the reason people don't, my retirement savings example is pretty fucking compelling, right? Save 15 years, you're better off than to save for the next 33 years. Why don't people do it? They don't do it because at a delta even arbitrarily close to 1, 50 years from now is irrelevant. Okay? You know, if you take, 0.9 to the 50, okay, it's irrelevant. Okay? Or if you do, even if it's 0.95, 50 years from now you don't care about. As long as you're somewhat impatient, the distant future doesn't matter. And that's why people don't save for retirement. Okay, that's why despite the incredibly strong incentives I laid out, people don't, because they discount the future. Okay? Questions about questions about that model. Okay, that's our standard economics model. That's what I grew up with. That's what you learn in basic economics. Okay, that's what you'll learn in the next level when you go on and do more economics. This is the model you'll learn. Okay? It's a multi-version version of the 2-period model I taught you. But it's wrong. Why is it wrong? It's wrong because every single psychological experiment ever run shows that discounting is not exponential, but rather hyperbolic. Which means that the discounting of the future is much, much steeper than we get from a pure exponential function. Okay? And here's the simple example of that. Okay? Let me say this example slowly. It's important to get it right. Imagine I offer you the following. Okay? $100, I offer you a choice. $100 today or $125 in a year. $100 today, $125 in a year. You can just don't vote, just think how you feel about this choice. Then I offer you a different choice. I say $100 in 2 years versus $125 in 3 years. Now, with this exponential function, that's the same choice. It's only a 0.9 factor between them. It's a 1-year gap. So it shouldn't matter if I offer you today versus 1 year or 2 years versus 3 years. It turns out it matters enormously. People always take the this year, but they'll delay it in the future. That is, people are impatient today, but willing to be patient in the future. And that is an illustration of self-control problems. That when it's about having your hot little hands, you want it. If it's about, well, will you save in the future? Sure, I'll save in the future. That's great. Happy to do that. Okay? And this example is exactly why this exponential model is wrong and the hyperbolic model is right. That basically people feel differently about today than the future. And so an economist named David Laibson at Harvard said, look, let's make a simple tweak to this model. Let's rewrite utility as the utility of today is today's consumption, C, plus a factor beta times the sum from tomorrow, next year, till the end of time, times C times delta to the I minus T. I minus T. Okay, how is this different than this? All I've done is I've pulled out today and add an extra factor B to the rest of the future, beta to the rest of the future. So look at this function versus this function. All I've done is pulled out one C from the sum, kept the rest of the sum, and add extra factor beta in front of this. What is that doing? That's saying that starting next year, I'm an exponential discounter. But with beta less than 1, that entire future is worth less today than it would be under an exponential model. Okay? So let me do this in a simple example. Okay? Let's say that you have, let's say that you're offered 100 today versus 125 next year. Okay? And then, as I said, so 100 in T versus 125 in T plus 1, and 100 in T plus 2, 100 in T plus 1 versus 125 in T plus 2. Well, for this decision, you use this part of the term, which is the same as exponential. So as long as delta isn't very small, you're going to wait. So let's say delta is 0.9. So that says that next year's is worth 125 times 0.9, which is still greater than 100. So you'd say, I'll wait. But for this decision, you've got delta and beta. And the best estimate in the laboratory of beta is 0.6. So now it's 125 times 0.9 times 0.6. Because you've got the regular delay of a year, but you also have this extra factor, which is you really like it today and care less about tomorrow. So now you reject the offer. And that is a simple parameterization of how you could reject this offer but accept this offer. You reject this offer because this offer is an extra feature that discounts at beta. Okay? That is how a very smart economist builds a psychological insight in a relatively simple way into one of our models.